Hello students, the question is a small hole of area of cross section 2 mm square is present near the bottom of a fully filled open tank of height 2 meter. Taking G equals to 10 meters per second square, the rate of flow of water through the open hole would be nearly, the options are given. To do this problem, we have to first understand what is Bernoulli's principle. Now it comes from principle of conservation of energy we know. Let us draw a flow tube like this, and this is a fixed horizontal ground. A is one end and B is the other end. Suppose velocity of flow at this end A is V1 and velocity of flow at B end is V2. The flow tube is filled with liquid. Height of A from the fixed horizontal ground is H1. Height of B from the fixed horizontal ground is H2. Superincumbent pressure on A is P1 and on B is P2. Assuming this is an ideal fluid, that is incompressible, we can say that the density of the liquid at cross section A is same as the density of liquid at cross section B. Now according to Bernoulli's principle, we can say that the sum of kinetic energy, potential energy and pressure energy per unit volume should remain constant at any cross section of the flow tube. Now kinetic energy, what is the normal formula of kinetic energy? Half mv square. So kinetic energy per unit volume will be nothing but half rho v square. Potential energy, normal formula mgh. Potential energy per unit volume is nothing but rho gh. Now pressure energy is given by external pressure into volume. So pressure energy per unit volume is nothing but pressure. So according to Bernoulli's theorem, the sum of these three quantities should be constant at any cross section of the flow tube. Therefore I can say that for cross section A, the total energy is given by half rho v1 square plus rho gh1 plus p1, and for cross section B of the flow tube, the total energy similarly is given by this half rho v2 square plus rho gh2 plus p2. Therefore from Bernoulli's principle I can say that half rho v1 square plus rho gh1 plus p1 should be equals to half rho v2 square plus rho gh2 plus p2. Now mind it, this formula is not always true. It is true only for an ideal fluid which is incompressible in nature, and also for non-viscous fluid. We are assuming that there is no liquid friction. Now using this, there is a special application which is known as Torricelli's theorem or velocity of efflux. Let us get into that. Velocity of efflux. Suppose we have a container like this, and the container is filled with some liquid. Total height of the liquid in the container is capital H, and we make a hole here at a depth, suppose h, small h, from the free surface of the liquid. Now the process is, we want to find the velocity of the fluid coming out of this orifice or hole, and this velocity is known as velocity of efflux using Bernoulli's principle. Okay. Let us first assume that this is an imaginary flow tube connecting this end, that is the free surface end of the liquid in the container, and this end which is the end at which we have made the orifice or hole. Therefore, for cross section 1, suppose this is the cross section 1 and this is the cross section 2. For cross section 1, let us write the energies. For cross section 1, kinetic energy is half into rho into 0 square. Now, why 0 square? Because we are assuming that the whole area of cross section of the hole is very small. So, the free surface of the liquid has very negligible downward velocity. So, this is an approximation, half rho v 0 square plus potential energy. Potential energy, this is the fixed horizontal ground. So, height is nothing but capital H. So, rho g capital H. Pressure, what about pressure? I have already told that this pressure is not the pressure of the liquid, but this pressure is the superincumbent pressure. The superincumbent pressure is nothing but atmospheric pressure. So, atmospheric pressure. This is the total energy at cross section 1 as shown in the figure. Now, for cross section 2, the total energy will be half rho v square. V is the velocity of efflux. Height should be calculated from the fixed horizontal surface. So, the height is capital H minus small h, that is this thing. And pressure, what about pressure? Pressure is nothing but, there is a hole, so pressure is nothing but the atmospheric pressure. Now, this is the total energy at cross section 2. Therefore, according to Bernoulli's principle, we can equate these two expressions, and we will get rho g h plus p naught equals to half rho v square plus rho g h minus h plus p naught. P naught cancels out. So, finally we get that this velocity of efflux is nothing but root over 2g small h. Remember, this h is not the height from the ground, this h is the depth of the orifice or hole from the free surface of the liquid in the container. I hope you understand this. Now, we are coming to this question. Here in this question, a small hole of area of cross section 2 millimeter square, that is the area of cross section of the hole is given. Now, what is the purpose of that? We will come to this later. 2 millimeter square, that is 2 into 10 to the power minus 6 meter square. We want to do the problem in SI, and a hole is made at the bottom of the tank. The tank is of height 2 meter. Therefore, I can say that, and the tank is fully filled with liquid. Therefore, here the small h is nothing but the entire height of the liquid in the tank. So, this is 2 meter. Therefore, I can say that the velocity of liquid emerging from here is nothing but root over 2 gh. Let us first put the values. 2 into g is 10, h is 2. Now, taking approximation root over of 10, we can assume that root over of 10 is almost 3. So, that is nothing but 6, almost 6 meters per second. Remember, we do not have any calculator to calculate this. So, we can take almost 6 or slightly greater than 6. This is the velocity. This is the velocity, mind it, this is the velocity of the water coming out of the hole. But in the question they ask you to find the rate of flow of water through the hole. Now, what about rate of flow? Now, rate of flow means, first understand what is rate of flow. Rate of flow means the volume of liquid coming out per second through the hole, correct. Now, volume of liquid coming out per second through the hole is nothing but area of cross section of the hole into velocity of efflux. A is what? Area of cross section. In the problem, area of cross section is given as 2 into 10 to the power minus 6, and velocity of efflux, area of cross section 2 into 10 to the power minus 6, and velocity of efflux is 6. So, the answer should be nearly 12 into 10 to the power minus 6 meter cube per second, that is volume per unit time. Now, only one option is near to this. So, option 3 is correct, which is 12.6 10 to the power minus 6. You can explain why the answer is slightly greater than my answer, because here I take the approximation that root 10 is 3, but it is slightly greater than 3. So, the actual answer should be slightly greater than the answer I get here. So, option 3 is correct. Thank you for watching this video. Please subscribe my channel Faisal.